All right, my children, here we go. Section 7.7, separation of variables, but these are now particular solutions rather than general solutions that we did in the last section. So the beginning part of what we're doing is very similar, if not the same, as what we did back in section 7.6. But this time they give us added information so we can find what C actually is, so that we have a specific function that goes with that particular differential equation. So I'm looking at this first one here. It's kind of not set up very pretty. It says find the solution to the differential equation xy quantity squared with an initial condition of y1 equals 1. So I'm going to change the way that this looks just slightly before I set it up to separate the variables. This would be the same thing as x squared y squared. So I have two separate pieces. They're not kind of combined together in the same set of parentheses. That's going to help me to be able to separate them. So remember, if I'm trying to move this y, it's being multiplied, so I'm going to have to divide. So here's what it's going to look like. It's going to be dy over y squared. And if I have this x squared staying where it is and move the dx over, it'll be x squared dx. Set it up to integrate. All right, so this would be y to the negative 2 dy equals x squared dx. And I say, all right, I can integrate that. That's okay. Here I go. Integrate, integrate. This becomes a negative 1 over y equals x cubed over 3 plus c. Remember, the plus c has to go on the right-hand side there with the x's. Now there's a couple things I can do. I have choices at this point. Once I have it integrated, I can figure out what c actually is using this information, or I can turn this into the y equals that it should be. Sometimes it's easier to find the c right at this place right here. So let's try that. This coordinate right here, this point right here, tells me that the x is 1 and the y is 1. So if I replace them, that's going to be this. Now what I'm trying to do here is find c. All right, that's what I'm working on. So I have negative 1 over y, which is 1, equals x cubed, 1 cubed over 3 plus c. Or negative 1 equals 1/3 plus c. And so when I bring this 1/3 to the other side, it's 1 and 1/3, so c is negative 4/3. Well, you normally don't see it as 1 and 1/3. So let's go back to our equation, which was here. I have negative 1 over y equals x cubed over 3 minus 4/3. We know the trick to do that flippy-do, but let's put this together. These are common denominators, so I can put this as one single numerator, which is going to make me be able to do my proportional rules. So negative 1 over y equals x cubed minus 4 over 3. So the next thing that I want to do is I'm trying to dig towards the y. This negative sign is a bit of an issue. So before I pull my rules for proportions, let's change this over here. So if I multiply both sides by a negative 1, that changes this to a negative x cubed and this to a positive 4. Do I need to change the 3 also? And the answer is no. Because remember, negative signs, they either go with the numerator or the denominator or out in front. So you've got a choice of where you want to put it. But here's where I'm going to go with it. 1 over y equals, this becomes a negative, this becomes a positive. It's going to make this 4 minus x cubed over 3. Hopefully that doesn't freak anybody out. But I changed the sign. This is now positive, and this is now negative, and so that takes care of that negative sign. And now I'm ready to do the flippy-do, because I've got 1 over y, I want y. If I flip this side, I got to flip this side. And that's my answer. I'm done. I figured out what c actually is. It's a particular solution. They gave you what the slope field looks like. So I've got a coordinate at 1, 1. If I were to be at 1, 1, you can kind of see how this guy goes. Remember, you're staying inside the cattle chutes for it. But it's this one's kind of weird. And you wouldn't know it unless you drew it on like one of those slope field calculator type things. On the lesson video, he actually did that. he showed you on the lesson video, but it kind of goes like that, because if you see it, it asymptotes right in here. I didn't asymptote very well, did I? I've got an erasable pen. I'm going to make my asymptote prettier. It goes like this. So there are programs out there on the internet that allow you to draw slope fields. Your calculator will do it too, but it takes a bit of doing to get to that particular feature on it. If you're interested though, Google search making slope fields on a TI-89 and you'll be able to see exactly how to do it. But anyway, that's what that one does. Most times they don't ask you to draw the particular solution, but in this case he gave you some examples that show that. All right, that's it. That's example 1. Example 2. Find the solution y equals f of x to the differential equation dy over dx is 2x over y with an initial condition of f of 2 equals 1. So again, they're giving you enough information to find c. Let's get there first. We need to get the y equals or something like that. So I'm getting the y's on the left, the x's on the right. This is a straight up cross multiplying. So I have y dy equals 2x dx. And that's easy peasy. I'm ready to integrate. No extra steps needed. This guy becomes a y squared over 2 equals, this guy becomes a 2x squared over 2 plus c. 2's cancel. So I have now a y squared over 2 equals x squared plus c. I'm digging towards the y, or at this point I can plug in my point. I'm going to dig one more step. I want to get rid of this 2, so I'm going to multiply both sides by 2. Y squared equals a 2x, 2x squared plus 2 times c is still a c. Let's plug it in. Y is 1. 1 squared equals 2 times 2 squared, my x value. Remember, this is your x, this is your y, plus c. If I have 1 equals 2 squared times 2 is 8 plus c. Bring the 8 over, c is negative 7. So go back to your equation where you had left off. Y squared equals 2x squared minus 7. Put your c in. I want y, so I've got a y squared. I am going to y equals plus or minus the square root of 2x squared minus 7, but it can't be both. And here's how you decide which one it is. Go back to the coordinate they gave you. If they didn't give you the coordinate, if you noticed in that last section, we left it as plus or minus, and that was the best we could do. But this one we can actually figure out, if you think about it, whether it is the positive side or it's the negative side. And so I go back here and look. Well, what's the y value? It's a positive 1. So because it's a positive 1, then this has to be the positive square root of 2x squared minus 7. If this had been a negative 1, then you would take the negative side. So it's the y that determines, maybe I'll circle those two in orange so that you can see that they're the reasoning right here. Because this is a positive y, this has to be a positive square root. If this were a negative y, this would be the negative square root. And so I come over here, and I'm looking at the slope field. Where's my point? It is at 2, 1. What would this thing look like? Now, don't draw this until after I've explained it and can talk about it a little bit. If I were to draw this, remember you kind of stay in the cattle chute here. Kind of goes like this. It looks almost like a hyperbola. Hyperbolas are sideways parabolas. But that's what it would look like. But I only want, and even if you think of square root graphs, right? If this were a square root graphs start and then they kind of go off to the side. This is what I have a picture here of, and what I've drawn currently is the plus or minus. I've got both of them. Because the regular old square root graph would start at the x-axis and then continue off to the right. So in this case, because I'm only looking at the positive side, the right answer is just that part right there above the x-axis. Which makes sense because it's a square root graph. Okay. There you go. That's your picture. All right, next example is, this is actually the last example. Find the solution to the differential equation with an initial condition of 0, -1. And you say, okay, well, that's not really a whole lot different than the ones we've done up above. So this is the same format. Get the x's on the left. I'm sorry, the x is on the right, the y is on the left. This y plus 2 grouping, to get that carried over to the left, I'm going to have to divide by it. So I'm going to have 1 over y plus 2 dy, or dy over y plus 2. They're kind of one and the same thing. I guess I'm kind of going a step ahead to get it ready for integrating. You're going to divide by y plus 2. Here's what it looks like. You have an e to the x dx on the right. All right, we're ready to integrate, integrate. This guy gives me 1 over anything is ln. So this guy's going to be an ln of y plus 2. On the right, e to the x is e to the x plus c. Now I can figure out what c is at this point instead of digging out. Remember, you got the initial condition, you have lots of choices. Eventually I'm going to have to get the y by itself. But let's see if we can figure out what c is while it's still somewhat simple, because if you think about what the next step's going to be, the next step is going to be me to have to loop this thing. So I'm going to take e, raise it to this power, and then come back equaling y plus 2. Because I'm trying to undo a logarithm, I have to turn it into an exponent. So thinking ahead, that's going to get a little complicated. Let me figure out what c is first. Oh my goodness. Say hi to Levi. ln, I have my x, oh gosh, my x value is 0, and my y value is a -1. So here I go, ln. He sees a doggy walking by. I think he's trying to say hi or something like that. All right, -1 plus 2. E to the x is e to the 0 plus c. So I have the ln of 1 equals 1 plus c. Do you remember what the ln of 1 is? So if I raise something to the 0 power, I get 1 out. That means my c is a -1. All right, so let's put that together back at my step right here. ln of absolute value of y plus 2 equals e to the x minus 1. Now I have to dig for y. I want to solve for y. So I'm going to remember that I'm trying to undo a logarithm, which means I need exponents. Here's my e. I'm going to loop-de-loop. Here's what it's going to look like. E to the, this is really weird, but it's true, e to the x minus 1 equals y plus 2. And so if I want to get y by itself now, all I need to do is subtract 2. And so here's my final answer. Y equals e to the x minus 1 minus 2. All right, now he went into a whole explanation on because logarithms are plus or minus, because absolute values are plus or minus, it could be, this could be a plus or minus situation, and it got really kind of complicated. So I'm just going to leave it be that this is the final best answer, and we're going to keep it there. My point was 0, -1. Let's see what the slope field would look like. There's 0, -1. If I were to draw the graph this time, staying within my cattle chutes, and it goes up like this, right? And over like this, and there it is. So there's example number 3. All right, we're going to go to the next page and pick and choose a couple of practice problems. I'm on this page. Let's pick I want to do one of the trig ones because you always pick me the trig ones, right? Let's go with number 3. Number 3. I'm only picking it because it's got the trig going on, and I know you guys love it. All right, so I'm getting the x's on the right, y's on the left. That means I'm dividing by y. So dy over y equals sine of x dx. which means I'm setting it up to integrate. 1 over y dy is the sine of x dx. And then what I want to do is integrate once I get it set up. Okay, y's are on the left, x's are on the right. Integrate, integrate. 1 over y is the ln of y equals, and if I integrate sine, is it positive cosine or negative cosine? And you say negative cosine. Plus c. Again, I'm going to have to write this as a y equals, but they gave me information to find the c, so this might be a good stopping place for me to be able to find that c. So, if x is pi over 2, y is 2. ln of 2 equals negative cosine of pi over 2 plus c. I did not do it this way when I did it on my practice problems. Let's see if it works out pretty though. All right, ln of 2 equals negative cosine of pi over 2. So if I'm up at pi over 2, I'm at the point 0, 1. Cosine is the x, so this is 0 plus c. So that would mean my c is equal to the ln of 2. I'm going to keep going with it and see what happens. I know what c should actually be, which isn't necessarily the ln of 2, but I also waited and figured out what y was first. So let's keep going. So I'm back here. This is ln of y equals negative cosine of x, negative cosine of x, and then it's plus the ln of 2. All right, in order to solve this, to get the y by itself, I'm going to have to raise it to the e, like take the e, do the loop. So my e base is here, and my loop would look like this. E to this power comes around to the y. So I'm going to have y equals a negative cosine of x, actually e to the, can I fit it in this? I'll make it pretty. Hang on. I got all discombobulated. All right, e to the negative cosine of x plus the ln of 2. And that's what y equals. So I'm good with this. Y equals e to the negative cosine of x. But remember how if I'm adding exponents, I'm multiplying by like bases. So this would be like times e to the ln of 2 if I separate it, right? Adding exponents separated as 2 like bases. E's and ln's undo each other. They're inverses of each other. So this really equals 2. This value right here equals 2. And so my final best answer for this question is 2e to the negative cosine of x. All right, let me show you how I did it when I did it originally. So I came down, I got to the same place, but instead of me solving for c at this location like we did, I kept going and got my y equals, and then I solved for c. So same answer, just a different approach. So I guess the point I'm making is it doesn't make a difference if you stop after you integrate and find your c, or if you wait until you get your y equals and then substitute and find your c. So this is done waiting for my y equals, where this was done just after I integrated. But same answer in the end, and we're good to go. All right, so there is a problem with trigonometry involved. Let's see if there's another one we should do. I think I'd like to do number 8. Number 8. Find a particular solution to this guy if y equals 1 when x equals 0. sketch the graph of the particular solution on the slope field. Okay, well, that's what we've been doing all day. So here we go. X is on the right, y is on the left. I've got to divide by y squared. That means I'm going to have 1 over y squared dy equals multiplied by dx, so x dx. And so really I have y to the negative 2 dy equals x dx. And there I am. So now I'm ready to integrate. Here we go. Integral of y to the negative 2 is negative 1 over y. Integral of x is x squared over 2 plus c. I can keep going and figure out what y equals, but I'm going to stop and figure out my c value. My c value in this case, x is 0, y is 1. So I have negative 1 over 1 equals 0 squared over 2 plus c. This is just 0. This is negative 1, so c equals negative 1. So I can go back to this place, and I can plug in the fact that it's a negative 1. So here I am. Negative 1 over y equals x squared over 2 minus 1. Can I currently do my flippy-do? And the answer is not quite, because remember it has to be a single fraction equals a single fraction, a proportion, for you to be able to play those proportion games. But I can change the 1 into 2 over 2. That'll let me combine them together. So negative 1 over y equals x squared minus 2 all over 2. Then I'm going to play the negative game. We saw that in one of the examples. This needs to become a negative x squared. This needs to become a positive 2. That's going to give me this. 1 over y equals positive 2 negative x squared over 2. And so I'm going to flip them. Get y equals 2 over 2 minus x squared. So there you go. I want to draw the slope field. Now the slope field for this one isn't what you think it would be. This guy comes in pieces. And if you think about it, you have asymptotes, vertical asymptotes at that, when the denominator equals 0. So you're going to have two values where the denominator equals 0 to have those vertical asymptotes. So this one, where's my coordinate? I have when x is 0, y is 1. So here's my coordinate right here. And I can see that that part kind of looks like a parabola if I follow those cattle chutes. But there's actually more to this graph. It goes like this. I have a vertical asymptote over here, and I've got another vertical asymptote to the right. And you might not know that unless you plotted points or something like that to come up with those values. Now, interestingly enough, again, I did this one different when I did it on your practice problems, like that I have posted. So let me just show you real quick. So I came down to this place right here, and instead of getting common denominators like we did, I kept going, and I figured out what C was. In this case, I have the values flipped though. I have the squared value first, so it's negative, and the whole number second, which is positive. So this is an alternate form. That's really what I wanted to show you. This is an alternate form to what we got. I think the way that we just did it together looks a little bit easier than what I did when I was doing it myself. All right, so here you go. There you go. Final good answer. Let's see if there's any others we want to look at here. All right, let me take and do number 11. This is a doozy, but let's end with this guy. I know there's several parts to it. That's okay. First thing, consider the differential equation. By the way, this is a question that you could see being on the actual exam itself. So it's got multi-parts. This would be like a free response question where they're asking you a whole bunch of different things and pulling in information that you learned from other sections. So this is classic, which is why I might as well go through this with you, because this is really a good question to get your mind thinking. Consider the differential equation of dy over dx equals 6 minus 2y. Let f of x be a particular solution to the differential equation with the initial condition of f of 0 equals 4. And you say, yeah, I've been doing that all day. Write an equation, though this is different, for the line tangent to the graph at x equals 0 and use the tangent line to approximate 0.6. Do you see how that's something totally from the past? A blast from the past. But we know to find a tangent line, we've been doing that since the very beginning of the year, you need a point and you need a slope. Well, they gave you the point. They gave you the point being 0, 4. Right here. And funny enough, they gave you the slope. They just gave it to you in a different form you're not used to seeing. The slope is dy over dx. The slope is the derivative. So that is 6 minus 2y, in our case 6 minus 2 times 4, gives me a slope that's negative 2. Now, can you put together for me the equation of a tangent line? And you say, yeah, that's easy peasy from years ago, squeezy. Right, here it is. I have y minus 4 equals negative 2 times x minus 0. Or, since it's kind of a simple one, y minus 4 equals negative 2x, y equals negative 2x plus 4. Any of those are perfectly good formats for leaving the line. You could have left it this way, that's fine too. Then the third piece, after you, well, I guess second piece, they want you to approximate f of 0.6. Well, this represents the x value. So you're going to toss a 0.6 in there for the x right here. And again, you can go to any of those formats. I want to know what f of 0.6 is, so plug a 0.6 in. Negative 2 times 0.6 plus 4 gives me negative 1.2 plus 4 gives me a 2.8. So f of 0.6 is about 2.8. You're making an estimation off that tangent line. So they're pulling in information for tangent lines. It's good to be remembered how that works. Part B says, all right, find the value of d squared y over dx squared at the point 0, 4. Is the graph of f concave up or concave down at this point at 0, 4? Give a reason for your answer. So now they're not even talking these differential equations so much. They're looking for, this notation means the second derivative, which goes along with what they're asking you. Second derivatives are the ones that determine if it's concave up or concave down. Do you know the first derivative? And you say, yeah, I know the first derivative. It's right here. They gave it to me right there. So if dy over dx, first derivative, is 6 minus 2y, what's the second derivative? D squared y. This is a Leibniz notation. And because we're in differential equations, we kind of keep it there rather than using y prime, y double prime kind of stuff. All right, so Leibniz, yeah, we can do that. Second derivative. What's the derivative of this? And you say, oh, that's easy. That's a negative 2 times y prime. Well, do you know what y prime is? Sure you do. It's right here. This is y prime. That's y prime. You're going to do a little substitution in there so that you're saying d squared y, second derivative, over dx squared is negative 2 times 6 minus 2y. They want to know, is it concave up or concave down at this point? Well, at this point, my y value is 4. Plug it in. So, second derivative equals negative 2 times 6 minus 2 times 4. Let's see what it comes out to be. You have 6 minus 8 is negative 2. Negative 2 times negative 2 equals a positive 4. And really all you care about is it positive or is it negative? And we know it's going to be concave up because your second derivative, I'll put it here, d squared y over dx squared is greater than 0. We gave a reason for our answer. There you go. All right, again, bringing back things from the past. All right, now we're getting into the current day, specifically this day. Find the function y equals f of x, the particular solution to the differential equation with the initial condition of f of 0 is 4. So we're going to go through and we're going to do the same thing we've been doing. So here's my differential equation. I know I kind of have it off the screen at the top, but anyway, this is what it is. This is all one piece. I can't separate it. It only has a y value, so I know this is a little awkward looking compared to some of the ones we've done. But it's going to be, if I get the y to the left, it's going to be 1 over 6 minus 2y dy equals dx. There are no x terms. Okay, so now I'm ready to integrate. This is where it gets a little dicey because we haven't seen one quite like this. But we know 1 over something is the ln. The ln of the absolute value of 6 minus 2y. However, see how if I take the derivative of this piece, negative 2y, and so far in all of them it's just been a regular old y where I haven't had to do this. So this one actually has a coefficient on the y that's other than 1. So I would then, if I took the derivative of this, I would multiply by negative 2. Well, I'm integrating. I'm going backwards. So instead of me multiplying by a negative 2, I am dividing by a negative 2. And that's going to be my piece there, which is a little bit complicated. And if I have the integral of a dx, that's just an x. Remember, I'm going up a power. So this would be an x plus c. Well, this whole negative 2 gets me all freaked out. So what I'm going to do is I'm going to take that guy and I'm going to multiply it over here. So I get the ln of the absolute value of 6 minus 2y equals negative 2x. Negative 2 times c, it's still a constant. And now I have it set up so that I can do my loop. Here's my e. I'm going to loop it around. And so it's e to the negative 2x plus c equals 6 minus 2y. I'm going to dig to get to my y. So the first thing, actually I'm going to make this prettier first. Do you see how this is? This is e to the negative 2x plus plus the c, so it's going to be times e to the c. Remember how we've seen that in other sections? If it's e to the c, that's still a constant. So I can rewrite this a little simpler as ce to the negative 2x. And again, we saw that in previous questions. Ask me in class if you don't catch that. I want to dig to the y, so subtract 6. Ce to the negative 2x minus 6 equals ce, let's see, we just moved the 6 over, and so that's going to give me a negative 2y. And now I'm going to divide everybody by a negative 2. Right? Everybody's got to get divided by that negative 2. So if I do that, I might do it individually. That'll be a ce to the negative 2x over negative 2 minus a 6 over a negative 2 equals y. And I guess there's not a whole lot else I can do to this thing. I've got y equals negative 1/2 ce to the negative 2x, and then this guy's going to be a plus 3. Did I figure out yet what my c was? I didn't. Let's see if we can do it from here. So my initial condition, I can figure out what c is. So let's take it and figure that out. If I plug in my y is 4, and I'm looking for c. My x is 0. What does c come out to be? My x is 0. I forgot to put that in. This is a 0. All right. I have 4 equals negative 1/2. This is e to the 0 power is 1, so this is a c plus 3. And so I'm going to take this 3, subtract it over here, I get 1. Multiply by 2. I multiply by 2, I get 2 equals negative c, or c equals negative 2, if I flip things around. All right, whew, let me go back to here. Plug in my c of negative 2. Luckily, this question doesn't take a lot of space. I'm going left here. I don't normally go left, but I did. All right, so I'm plugging in the fact that c is a negative 2. Well, now think about that for a second. Y equals negative 1/2 times my c of negative 2 times the rest of this hot mess. What happens up here? Negative 1/2 times negative 2 is a positive 1. So I get y equals just e to the negative 2x and then plus 3. And that's my final answer for this part. Ooh-wee. Could I have found c earlier? Sure I could have. Should I have? Probably. But anyway, we came out with the same answer there. So that's my final best answer for part C of number 11. Last part. Now they're bringing in limits, and you have not talked limits for forever. So find, for the particular solution, which is this guy, find the limit. Well, here's how the limit goes, right? The limit, as n approaches infinity, for this function, I'm going to write it a little differently. E to the negative 2x is like 1 over e to the 2x plus 3. So that when I plug in the infinity, it's going to make a little more sense. So if I put infinity in here, 2 times infinity is infinity. E to the infinity is a really big number, but it's 1 over that, so really this is like 0. So this becomes a 0 when I plug infinity in, and 0 plus 3 is 3. That's my limit. So you can see this question is a great AP example as a free response because it talked tangent lines from back in the beginning, it talked concavity, second derivatives, it talked differential equations, particular solutions, and it talked limits. So all sorts of crazy things with this, but it's a really important question. All right, you are set to go. Oh, by the way, numbers 12, 13, and 14, if I didn't say this already, they are optional. I did include the answer key to them if you felt like doing them. I just right now on our time crunch, I don't want to get too crazy, and so we're going to leave those off. Like I said, that number 11 that we just did was a great example of an AP question. These are also good, but again, we're going to kind of keep things a little bit on the lighter side so that you don't get too bogged down. All right, I will see you in class. Shoot me an email if you've got questions. Thanks for your hard work.